Anybody have any questions about anything before we get back into volumes? All right, so we left in the middle of this example, so kind of reset. I have this region bounded by these two curves. I'm trying to find the volume when I revolve that around the y-axis. So it looks like where we finished, we found the x values where, yeah, we found the x values where these two functions intersect. Where do we go from there? So we did not draw a graph last time. So this area right here, we're trying to revolve around the y-axis. I believe we found these x bounds were 1 and radical 3. Okay, so how do we keep marching towards finding that volume? If we're revolving around the y-axis, what does that mean about the integral we're about to set up? It needs to be in terms of y, right? So even though we found the bounds in x, I don't know if we can use them. What should our bounds really be then? So this point right here is going to have coordinates of 1, 4. And this right here is going to have coordinates of radical 3, 3 plus radical 3. What's that? Oh, did we go the wrong way? Okay, so let's think about it. So we found our u values were 1 and 3, right? Then x values should be squares of those. Can I erase what I did last time? Weird. Okay, so x should be 1 and 9. So then this point is 9, 12. That makes more sense. Okay. So what should our bounds of our integral be that we're about to set up? Should be 4 to 12, right? All right, so now we need to try to figure out what the rest of this integral looks like. We're revolving around the y-axis. So the question we really have to answer in the end is which function gets subtracted from which other function? So in this case, what is the greater function? More importantly, how do you find it? It's not gonna be the one on top, because here's the subtle thing here is it's gonna be one further to right, because basically these two things here are, we're integrating in terms of y, which means we're integrating functions that basically give us x values. They're x as function of y. So if they're x as function of y, then I want to talk about the one that has the greater x values. That's going to be the one that lands on the right. So I know it's kind of a subtle thing, but it's very, very important. So let's talk about it as long as we need to. Any questions about why I want to subtract the further right function minus the further left one?
Which one would that be, the x plus 3?
Which one? The further right? Let's identify the further right. Yeah, which is the function on the right? Maybe I can exaggerate this a little more. That should not go behind the y-axis. So yeah, if I make that area a little thicker, yeah, the function on the right is going to be the line. The line has a By the way, I'm taking some liberties here. So I think I had this integral set up for if we're going to find an area. If we're going to find the volume, we're going to make some modifications, right? So what do we do to these two functions once I identify them? In other words, how do we find the volume using this washer method? I'm finding volume of cylinders, right? Go ahead.
You have to square the x with the x function.
Right. I also got to multiply them by pi, but I can take that out on the outside. So what is my outer function? My outer radius squared, my inner radius squared. Doing this with respect to y. So in this case, my outer function is going to be the line, but can I write it as x plus 3, or do I have to do something else? Got to be y minus 3, right? So basically, I have to isolate both of these equations. Isolate x in both of those equations. So y minus 3 squared minus what other thing? If y equals 4 radical x, then what do I get when I isolate x in that equation? So 1/16 x squared or y squared?
Yeah.
Yeah, let's just spell that out. If y equals 4 radical x, squaring both sides would be y squared equals 4 radical x squared. Y squared equals 16x. X equals 16 over y squared. 16 over y squared? No. No. Y squared over 16. All right. Are we good with that integral as it is set up?
So did you apply like the square on this second one? Okay, yeah.
No, I meant to. Good catch. Is the integral now correct? All right. I think we agreed last time that we would set it up and walk away. Is that okay, or would we like to finish it? Okay, I'll leave it set up. Yeah, you can finish it on your own. I'll post these notes later, but yeah, I mean, like, I think the most important thing here is setting these up. But I believe you could evaluate them as well. Now let's move on. So the last thing I want to talk about from this section is, so all the solids we've talked about so far and how to find their volumes are these solids of revolution, these things that we find when you take some two-dimensional area and revolve it around a straight line to get a volume. We can also use integrals to find volumes of solids that aren't made that way. So this weird shape that I want to talk about now, basically, here's the way this thing is kind of formed. It's kind of looks like a clamshell. The base of it is a unit circle, essentially. It's a circle centered at the origin, radius 1. But if I were to cut down, and maybe those straight lines that are kind of on the surface here, try to illustrate that. But if I were to cut like perpendicular to the height of this thing, we would get equilateral triangles. So let me just draw like one of those. This will be a little bit tilted because I'm trying to mimic the projection here. But basically, if I cut down, if I take a cross section there, no matter where I take a cross section, I'm going to get an equilateral triangle. So even though those triangles are going to have all the same lengths, I'm going to get a different size triangle depending on where I cut this thing, right? So if I cut near to the center, it'll be larger than if I cut near to, the front or the back. So are we okay with that description of this solid? Okay. So how do I find the volume of things like this? Even though this is not really a prism, we're going to treat it like it is. Because, this thing right here that I drew is a flat two-dimensional thing. But if I give it a little bit of a dx width to it, where I'm basically keeping the other dimensions constant, then I get to treat this as like a triangular prism. So the way we find volumes of prisms is whatever the area of the base is. If I multiply that by the height, then I get a volume. Do we know how to find areas of equilateral triangles? Or really of any kind of triangle? Yeah, so the area of a triangle is 1/2 base times height, right? So now what I would like to figure out is how to relate base and height like how to relate those to x. So if it's not clear from that diagram here, basically the center of this circular base is right at the origin of my plot. So that's gonna be really helpful for us in terms of setting up these base and height functions. So let's say the origin is somewhere hidden under here. And this kind of elementary example triangle I'm looking at is, a little bit forward, a little bit in the positive x direction. So for some x value, how would I find how long the base is of my triangle? So basically, I'm looking for the distance from here to here. How long is that?
The radius 1.
The radius of the circle is 1. But if I'm treating this as the base, like look at the way that I drew that arrow with, or that line with the arrowheads on it. What direction is that thing spanning? That's spanning the y direction, right? So the first thing I'm going to do, just to kind of build up to this, is I want to express that base distance in terms of y. Can we do that first? So for some given value x, like what is the value of y right here? Well, we don't know, but can I say that this length of the base is going to be double whatever that y value is? Because basically this, if I kind of project the y, or the x-axis going backwards and the y-axis going down the center of this circle, the base length is going to be how far to the right does this extend minus how far to the left does it extend. So basically y minus negative y. So for now, I'm going to say that the base is equal to 2y.
But, if we know like the radius, why is it not just like 2? If the bottom.
Because, okay, so basically I drew one triangle here, right? But let me draw like the maximally sized triangle, which is going to be the one that the y-axis cuts through. That's going to go all the way to the top of this solid. So yeah, I know this circle has a constant radius by definition. But where I make these triangles, those triangles are not going to be the same size, depending on where I decide, like where I'm looking. Because basically to find the volume of this thing, I have to integrate basically over some interval, over whatever we find our bounds to be. So because of that, like I know that these triangles are always going to be equilateral, but I don't know they're always going to be the same size. Because, what if I take I didn't really leave myself enough room, but if I were to think about the triangle I would make very near like the front end of this shape, those are going to be very small.
Oh, okay.
So that's why I have to leave it variable, because my triangles are going to be different sizes depending on where they live. Go ahead.
Just thinking about like the biggest triangle would probably be like when y equals 0.
That's true.
So would you do 2 minus 2y in that case? Because if y is 0, then the base is 0 in that equation. Or is it?
Right, so. Basically, we're gonna set let's keep on going. Maybe us keeping going will answer that question. What I'm marching toward, and I think we could do this either way, but what I'm marching toward is an integral that's in terms of x. So I want to express y in terms of x. So let's go ahead and do that now. Do I know anything about the relationship between x and y based on the description, the definition, the way this solid is made? So like if I pick a y value like here, can I find the x value that goes with it? Let's say that y value is 0.2. Could I find the corresponding x values so we're going to respect that radius of 1? So let's go way back. What makes a circle a circle?
Oh, x squared plus y squared equals r squared.
That was what I was going to work toward, but a circle is a thing that has every point on a circle is the same distance from a fixed point, right? So, I mean, my fixed point is kind of been buried underneath all my annotations, but there's my fixed point that all the points on my circle have to be the same distance from, right? If I pick a bunch of XY points, how do I find the distance between these points and my center?
It's the same.
It's the same, right? But like, how do I find the distance between 2 points in 2 dimensions? This is getting so messy, but I think it's good. Can't I model all of these as right triangles? Then I can take their x distances, their y distances, and find their distances as hypotenuses. So that's basically, that's where the x squared plus y squared equals r squared comes from. Is the fact that that's how a circle is structured. Every single point on the circumference of the circle has the same distance from the center, which is what the radius is. So that's the x squared plus y squared equals r squared is essentially the Pythagorean theorem. But in this specific case, what is my radius? 1. So I believe this is the way we can unite x and y. X squared plus y squared equals 1. Ask me all the questions about that. It was the journey to get there, which is fine. I expected it to be. Are we okay with x squared plus y squared equals 1? Can I now use that thing to represent the base in terms of x? If I know the base is 2y, can I isolate my circle equation? Can I isolate y in that? So y squared equals 1 minus x squared, or y equals radical 1 minus x squared. So I think my base in terms of x is going to be radical 1 minus x squared. 2 times that. So we got the base. Now we need to talk about how to find the height of this thing. So now let me just isolate one of these triangles. I think we said this was y, this was y. Which means these are 2y, right? All the sides have to be the same.
Wait, why is it 2 right.
Yeah. So I split up the base into y and y, but they're really all the side lengths are 2y. Can I represent that height in terms of y somehow?
Is it not like the hypotenuse or something if we turn it into triangle?
And so if you turn it into what, sorry?
Like if you split it in half, would it be like y squared plus 2y squared equals c squared.
You could use Pythagorean theorem. I think you might be off about what you're calling c squared. But something I could do is this. If I just looked at the right triangle part of this, straight lines. And calling this, basically, I'm going to call this B. Or I'll call H. That's the thing I'm trying to find. I do know that y squared plus h squared equals 2y squared, right? Is that fair? So y squared plus h squared equals 4y squared. So h squared equals 3y squared. So h equals radical 3 times y. So now if I substitute in for what I say y was equal to in terms of x, radical 3 times
1 minus
1 minus x squared. So now I have my base, I have my height. We said that to find the volume of this thing, we were going to integrate so we could multiply our area times our heights. In this triangle I drew a while ago, what was the height of this triangle essentially? I mean, not think of it as the thickness. I guess I'm using height for too many things. Area of the base times the depth, thickness, whatever you want to call it. So I think basically I have 3 dimensions here. To find the base length, I think I'm looking in the x direction, right? To find the height, I'm looking in the. Actually, that's I guess the z direction. I didn't really label it. So let's back up. Are we okay with how we express the base and height in terms of x? So let's start setting up this integral. Because right now I think we're equipped on how to find the area. The area is going to be 1/2 times the base, which is 2 times 1 radical 1 minus x squared times radical 3 times radical 1 minus x squared. So where's that third dimension come from? Where's the depth come from in this volume? That's going to come from me allowing change in the x direction. That's where the dx comes from. There's one last thing we're missing from setting up this integral. The bounds. Do I have any idea what the bounds are?
-1 and 1.
How'd you get -1 and 1?
So the maximum radius.
Right. So if I want to integrate over the whole circle, then yeah, it's a radius of 1. So x can be -1, so all the way back in that diagram, or all the way up to +1, which is all the way forward. So I think my bounds are -1 to 1. Any questions about where the integral as it's set up came from? Is this an integral we can deal with? Is there something we need to do before we start dealing with it though? Yeah, anything we can do. As you multiply them together, what do you get? So 2 times radical 3 times 1 minus x squared. So I think we get some things that cancel. This 2 will cancel this half. And then I'll also pull out the radical 3. So what's left is this. So we've come a pretty long way. Let's talk about how we got here as long as we need to. What questions do you have about any of the stuff we've done so far? Because a lot of it is very different from the way we handle revolved solids. Go ahead, Colin.
So basically what we're doing here is, we're finding the area of in each triangle along the interval,
Mm-hmm.
and then. The way it creates, I guess, we define the base of it as, in terms of the circles, so that
Yeah.
we don't have to really use the area of the base in that. Volume equals area base times depth equation.
We are using the area of the base.
And that's this.
Yeah, so basically, and it's there's ambiguity in what you call the base and what you call the height. But basically, if you were to slice this solid down, straight down into the XY plane, when you pull it apart, you're gonna have these cross sections that are in circles. Those circles, the triangles.
Yeah.
Those triangles are the bases I'm talking about. That's the area we set up. That's why our integral is, 1/2 times base times height. Okay. Because the things we're treating as bases are triangular.
But is it like, I'm confused, why are we using the equation for area if we're trying to find the volume?
Because of the way we think about prisms. So basically a prism is, this is a very thin one, but that is not detached. So this box right here is a prism, because, ignoring that little tab right there, no matter where I were to cut through this, like I cut through it here, it makes a rectangle, right? But no matter where I cut, it makes the same exact rectangle, right? So because of that, if I want to find the volume of things, how do you find the volume of a thing of this shape? Do you remember? Yeah, you just multiply all three of the lengths together, right? Length times height times width. Another way to think about this is I can just find the area of this rectangle, right? And then multiply it by how far back the rectangles go. That's the logic we're using here. If I can find the area of a base of this thing, and then I can multiply it by some depth. So what's the thing in our integral that represents the depth? That is basically the dx. So all this stuff right here, including the 1/2, that is how you find the area of a triangle. And then multiplying it by that little tiny dx treats it like it's a triangular prism with a very small amount of thickness to it.
Making it like the integral as well.
And then we have to use an integral because those triangles, once you pick a different x value, you would basically have a different size triangle to look at. That's why, because that's how we introduce all three dimensions and account for the fact that two of them vary.
Is it possible to find the actual volume with just one straight line function revolving around y axis and not messing around with those circle stuff? And bounce will be 0 and the height
So what area are you revolving around what line?
I mean, if you look at the that shape from side, it would be triangle, right? It would be a right angle triangle if we consider half of it. And if you take that long side, let's say two
So I'm not going to say no. I'm saying I'll say this. I cannot see a way to make this solid by taking a flat planar area and revolving it around an axis. So if you can do that, if you're envisioning a way to do that, then yes, you can find the volume that way. It's just not jumping out at me. But yeah, if you can figure out what that definition looks like, then everything we've done before will work. But if anyone sees a way to treat this as a solid made in that way, let me know. I'm not visualizing. So yeah, so if this is indeed a solid that cannot be generated that way, then basically we have to resort to other means. Yeah, the washer method and disk method they're for finding volumes of solids made by revolving them. Like revolving them in a full rotation around an axis. Go ahead.
Can I ask for like, do we need to figure out every time we're doing a fluid state? Like, or are we gonna go through the shape that we're gonna shoot?
I mean, this process is going to be limited to shapes you can deal with. So equilateral triangles and circles those are things you can deal with geometrically, right?
Yeah.
And I mean, we're not really dealing with the way we're dealing with the circle is, more analytically. Because we need to know where the coordinates are. But yeah, for these non-revolved solids, yeah, we need to stick with more geometrically friendly kinds of things. Any more questions about? Go ahead.
How could you put a bound that wasn't centered on the coordinate? Or
So-
what was that?
Basically, I mean, if I just handed you this solid and asked you to model it, I think probably the most convenient way would be to say, all right, this is a circle. I'll treat the center as the thing I'm going to call the origin.
Okay.
So basically, yeah, this object, basically I just want to find the volume of it. I'm not saying it is in any particular location. Like I could set this integral up with bounds of 0 to 2 and make some modifications that way.
Yeah.
But really all this centering of the origin and making the bounds from -1 to 1 is a convenience thing.
Okay, so
It's not like a requirement.
could you technically put any bounds so long as they're two?
As long as it's two units in length.
Okay.
But like you could do the integral from 4 to 6, but then you're gonna have to make modifications to the way that the base and height
Okay,
are functions of that. But yeah, you would still wind up in the same place we're about to wind up. Good questions. What else? Are we ready to integrate? Okay. So what is the integral of 1 minus x squared? Integral of 1 is x
Minus X cubed.
from 1 to -1. If I plug in 1, I should get 1 minus 1/3 minus all the stuff when I put in -1, -1 plus 1/3. So that comes out to be radical 3 times 2/3 plus 2/3, so 4/3. Or radical 3 over 3. Oh, no. So kind of a long way to go with that. Ask me whatever. Okay. I see some people copying. I'll take a minute here, but this is what I got for you for this section. So basically we've talked about 3 different ways to handle volumes. Disk method and washer method, which at least a couple of you argue are not different. And this method here for dealing with solids that are not revolution solids. So now we're going to move on to another way to find volumes. And that's this shell method. So how does this thing work? So just to kind of set the stage here, everything we've looked at so far, or not everything, but all the revolved solids, the way we set up the integral has something to do with the line we're revolving it around, right? So if we're revolving it around the y-axis or any vertical line, then we've had to set up our integral in terms of what? X or y. So So here's an area. If I wanted to revolve it around the x-axis or the y-axis, I have to set up an integral in terms of what variable? Has to be in terms of y, right? And it's similar if I revolve around the x-axis, right? I have to set that integral up in terms of x. So the shell method is basically gives us another degree of freedom. So now with the shell method basically works this way. If I want to revolve something around a vertical axis, I need to express it in terms of y. Or if I wanted to revolve around a horizontal axis, I need to express it in terms of x. So this thing right here, I want to revolve this around the y-axis, which based on everything we've done with volumes, if you want to revolve that around the x-axis or the y-axis, you need to set up an integral in terms of y. That won't always be possible, or maybe it will be possible, it'll be far more difficult. So the way the shell method works is this. I am still going to set up rectangles because that is where most things in integration kind of start. But now if I take this rectangle and revolve it around the y-axis, what is that going to give me? It involves circles, but it's a three-dimensional thing, right? It's a cylinder, but it's very, very hollow, right? So in the past, we've dealt with discs, which are solid cylinders, and we dealt with washers, which are solid cylinders with hollow cylinders punched out of the middle of them, right? Now what we're dealing with is this very, very thin cylindrical shell. So one thing I want to point out about the way a cylinder is shaped, it has three surfaces, right? And so far, what we've dealt with are basically the top and bottom, because, well, so what shape are the top and bottom of a cylinder? Those are circular, right? So everything, all the volumes we've dealt with for solids revolution have been basically, again, back to the whole prism logic, finding the area of a circle, multiplying that by some thickness to get a volume of a disk, right? But now we're not dealing with the circular part of a cylinder, we're dealing with the side face of a cylinder. What shape is the side of a cylinder make? It's a rectangle. I mean, and not obviously when you look at it look at it as it sits, but if you were to roll that out, that's a flat, you could, without deforming it, you can roll that into a rectangle. So we know how to find the areas of the circles. We said these areas were pi r squared, right? How do I find the area of the rectangle that I just made by rolling out that sidewall? It's height times the circumference, right? Basically, because the length of this rectangle is going to be identical to whatever the distance around that circle was. How do you find the circumference of a circle? 2 pi r. So the area of this thing is 2 pi times the radius times the height. So just like with discs and washers, we want to take a two-dimensional area and then multiply it by some thickness to give it that third dimension, to give it the volume. So I made this rectangle. This rectangle was, just to keep consistent, is dx wide. So would we agree that dx is the thickness of this rectangle? Because basically I'm wrapping this dx rectangle around the y-axis. So that's going to give me a thin cylindrical shell, right? If I unroll that rectangle, that longer rectangle I just made, I believe it has a length of 2 pi r. It has a height of whatever's calling h right now. But how thick is that really going to be? That's going to be that dx. So the way I find that volume is basically by integrating these areas. Over some change in x. So that's the thrust of the shell method, is one way I like to think of it is basically when you change your dx, you're kind of rolling the paper towels back onto the roll. You're increasing. Those things are aggressive. Any questions on kind of the setup here? Go ahead.
Oh wait, no, never mind. Radius and height are constants.
No, they won't be. They typically won't be.
So do you put them in terms of dx then?
Not in terms of dx, but in terms of x. Basically, so basically for some x value, like basically this is the way an integral works. You define an x value, and then like you take a height or do an area, you take the height at that point, but then you multiply that height times whatever your change in x is. When you're first learning to do this, you call it delta x because it actually has some measurement to it. But when we go start working towards integrals, we limit that to make it very small, so we call it dx. But yes, these radius and height things are, I'm going to say x, but really they can be in terms of y as well. They are functions of x. So this right here is the area of the side. So the area of a rectangle, and this dx gives that third dimension, the thickness. So why would we ever need this thing if we already have the diff method? So I think this function's a good example of why it's useful to have. But before I go from this slide, any questions about, maybe it's very hard to think about what questions you have. We're just working in generalities, but any questions about the way this has been set up so far? Go ahead. It's a height as a function of x or y. I mean, in terms of whatever the variable you're going to integrate on. So back to why this thing has this definition. Basically, the place, now that we're revolving a region around a y-axis, and we want to use an integral in terms of x to find that volume. So now, like using those combinations of things. So basically it's this combination: vertical axis and integrating on x. Or another way to say this, I have a vertical axis that I'm going to revolve around, but also like the slices I'm going to make on that area, those are vertical as well. Basically, the rectangles that I would make using dx there, those are all going to be vertical. So basically that combination right there is what the shell method is for. So for any given value of x, the height is going to be like, we'll treat the height as fixed. But as you like move throughout the shape, like if I were to make this rectangle here, then yes, I'm treating it like it has a fixed height for that value of x, but it's a different height than if I would have made that x happen somewhere else. So because of that, I have to treat the height as something variable. That's a good question. What would the height be for either one of those rectangles? Whatever that upper function is, right? Which I haven't told you. But basically, these heights are going to be y values. Which if you knew what y was equal to in terms of x, then you could make the integral. But I'm trying to keep that hidden for now. But very, very soon, we're going to find this volume. But for now, I'm just trying to use this as in generalities to kind of build up what the shell method is and where it comes from. Are we okay? What else do you got for me? The volumes are nasty. Ask me all the questions. Okay, so now maybe I should tell you what this is. So y equals 1 over 1 plus x squared. So if we wanted to find this volume by revolving around the y-axis using the disk method, I would have to isolate x, right? It's not impossible, but it's going to lead to an integral that's much nastier to deal with. So because of that, I am going to dictate that we stick to the shell method for this one. So how do we find the volume using the shell method? The volume is equal to 2 pi times the integral from over some interval of a radius function in terms of x times a height function in terms of x dx. So if I just took like a basic arbitrary rectangle here, I revolve this around the axis to make this very thin cylindrical shell. What is the radius of that shell? It should simply be the x, whatever the x value is, right? The radius of that thing is just going to be how far I am from x equals 0, the y-axis. So my radius should just simply be x. What is the height of any rectangle I decide to make here?
1/1.
So let's build that up. Yeah, so basically the height is just going to come from the y values for this one. But we have a way to relate x and y, so that's equal to 1/1 plus x squared. So we need to express our radius and our height in terms of whatever the variable is. I think we've done that. Are there questions about how we've done that? About what they are? Okay, now we can set up the integral. We're missing the bounds. Do we know what those are going to be? I think my writing is kind of, or my graph is kind of small, but can you tell what the right end of my area is? 0 to 1. So I'm integrating on all the x values between 0 and 1. And what is the function I'm going to integrate? X times 1/1 plus x squared. So 2 pi times the integral from 0 to 1 of, I need the dx for the thickness. x/1 plus x squared dx. Is this an integral I can do? How? U substitution? What would you want to use for u? Okay, if we do u equals 1 plus x squared, then what is du? 2x dx. We should probably change the bounds as well, right? So that becomes 2 pi times the integral of, what are our new bounds? 1 to 2 of 1/2 du over u. So if I solve this thing if I divide both sides by 2, then I get du over 2 equals x dx. But then if we do that, we can pull out the half, right? So then this becomes the integral, or pi times the integral of 1/2 of du over u. I promise that integral is a lot simpler than the thing that would have come up from the disk method. What's the integral of du over u? Oh, go ahead. Do you have a question, Colin?
But it is possible to use this method.
I think so. The only reason I'm not promising you yes is because I don't know what the integrand is going to look like from the disk method. So you might have to go to like a table with it, but that's possible.
And like on a test, you'd probably say you specify use the shell method.
I don't know. I'm not going to promise I would specify. I might leave it to you to decide. Like, if you start seeing that the integral that's going to pop up is going to be gross, then maybe that's a hint to go the other way. But I can't promise that I'll push you to do a certain method. Patrick, do you have a question?
I was gonna ask, how can you tell, like, whether you show them this or?
I think so. Besides the fact that I was kind of pushing us towards shell method here, the reason I was pushing us that way is because so we have y in terms of x given to us, right? If we were to isolate x here, let's start looking at it. Y times 1 plus x squared equals 1. 1 plus x squared equals 1 over y. X squared equals 1 over y minus 1. X equals the square root of 1 over y minus 1. I have doubts about my ability to do that. I mean, so I've already done more algebra than I had to do for shell method. I'm not even sure that the integral is going to be a friendly thing when I get there. So those are the kinds of things, those are the kind of considerations that are more like logistical. All right, so it's 9:55. So let's finish this thing off. What's the integral of du over u? Natural log of the absolute value of u. So I get pi times the natural log of 2 minus the natural log of 1, which is 0. So final volume should be pi natural log of 2. All right, I'm over time. I'm going to go ahead and stop here. If you have any questions, come talk to me. Otherwise,